side again. So what we're going to see today is how constraints and how the propagation are implemented. This is the last part. This is putting everything that we have seen together. So we're going to talk first about the constraints and then about the propagation. So the constraints have to implement two methods when you want to define a new constraints in the constraint programming system. So you have to have a post method and you have to have a propagate method. The post method is really saying, hey, you are adding the constraints to the constraint solver, and now you have to do the initial propagation and you have to link the variables and the constraints. That's what it does. And the propagate method is just doing the propagation, applying the filtering algorithm. And what I'm going to do now is actually illustrate that on two constraints, a simple one and a more complicated one. Okay? So once again, interface of a constraints, two method, post and propagate, amazingly simple. This is the core API. I will modify it a little bit when you try to make the propagation more efficient in the latest part of this video. So this is the constraint x is not equal to y plus c. Now this constraint, as you know, is only propagating when x or y is bound, when they have a single value, right? And so keep that in mind because this is going to be important. This is how we're going to implement the propagation here. If the two variables have multiple values in the domains, then this constraint is automatically true, satisfied, and there is no pruning that you can do. All right, so look at the slides now. You see what is highlighted is the constructor. Nothing really fancy here. You have the two variables x and y and the constant c. And the only thing that the constructor does really is storing these values so that you can use them in the post method and in the propagate method. So let's look at the post method here, which is interesting. So the first thing that it does is some initial inference. So if y is bound when you post the constraints, so you can immediately remove the value of y plus c from the domain of x. That's what you see in these first two lines. Y.min is the value of y because the min and the max are the same. There is a single value in the domain. You do the same if x is bound, then you remove the value of x minus c from the domain of y. This is the initial propagation. If the constraint is already one of the two variables bound, you can already prune the search space. There is nothing else to do. Now, most of the time when you pose these constraints, x and y are not going to be bound. And what happens here in the next two lines is extremely important. That's where you bind the variables, and that's when you link the variables and the constraints. So what you're saying here is, hey, variable x, when it's become bound, then it has to propagate this constraint. And same thing for y. Y, you tell y, propagate this constraints when you become bound. So what's going on behind the scene, obviously, is x is going to add these constraints in one of its lists of constraints that we have seen before, one of its stacks of constraints that we have seen in the previous video, right? So this is linking the variable and the constraints such that they propagate at the right time. Now the propagation here is extremely easy. It's essentially what we have done already before. If a variable y is bound, you remove the value of y plus c from the domain of x. Otherwise, you remove the value of x minus c from the domain of y. Now, there are only these two cases because we know that the only way this constraint can be propagated is when x or y are bound. So one of the two has to be bound at that particular point in time. Right? So this is how we implement the constraints, right? Initial propagation, linking variable and constraints, and then propagation. All right, let's look at something which is a little bit more complicated. This is x equal to y plus 1. And we are using a bound reasoning here. So remember, the first thing we did for the send more money problem a long time ago. And so what you see here is the post method, which is once again reasonably simple, right? So you test if y is bound, you can assign the value y plus 1 to x. If x is bound, you assign the value of x minus 1 to y. And otherwise, what you do is you call propagate. That's the initial propagation. I'm going to describe it in a moment. And then you link again the two variables x and y. But this time you don't link them when x or y are becoming bound. What you're doing is saying, hey, you have to propagate this constraint every time the min and the max of x or the min and the y of y is changing. So this is this propagate on bounds method that you see there. So every time the min or the max of x is going to change, you're going to propagate the constraints, and similarly for y. Now the propagate method here is also extremely nice. So what you are doing here is this kind of intersection reasonings that we had seen before, right? So what you do is that you compute the intersection of the left and the right hand side. So you compute the new min, which is the max of the min from the left hand side and the right hand side, so the min of x and y min plus 1, and you take the maximum of that because that's the intersection of the two intervals, and you do the same for the max. You do the min of the maximum of the left hand side and the maximum of the right hand side. Now you have the new min and the new max, and the only thing that remains to be done is to update this new min and this new max of x and y. Now, if during that process, min and you are actually updating the min of x or the max of x or the min of y and the max of y, then some other constraints are going to be put inside the queue and propagated, right? So this is what is happening. So this propagation here is going to be called every time x and y is actually being have their bounds being modified, right? So very important, this is what the propagate method is going to be called over and over again every time you modify a bound of x or a bound of y. All right? Good. So now you know how to implement the constraints. It's actually pretty easy, right? So you have a post constraint to do the initial propagation, link the variables and the constraints, and then you have the propagate method, which really implements the filtering algorithm. All right, good. So let me talk about the propagation now. We are ready. We are finally ready to see, to show you what the propagation does. And so the propagation here is orchestrating the whole process. We are adding the constraint, adding the objective, and computing the fixed point. Everything is in there. But you're going to see everything here is actually pretty small because we have built all the blocks that are needed for actually implementing the constraint propagation. Okay, so this is an interface of the solver. It has two parts. So the first part is really, the part which is used when we state the model. We are adding the constraints to the solver. We may be adding an objective function for minimizing or maximizing a variable or an expression. So that's the model construction part, and we won't talk about this because this is not really important. What I'm going to talk about now is the propagation API, how we schedule the constraints and the fixed point algorithm. So this is the implementation of the solver in MiniCP, and it has a couple of things that are interesting. The first thing it has, and that's what you expect, right? It has a propagation queue. That's where you put all the constraints that need to be processed, that need to be propagated, for which you need to apply the filtering algorithm. And then you have the post method for every one of the constraints, which is also interesting because when you post a constraint to the system, what the system does is actually posting this constraint, which means initial propagation, and then linking the variable and the constraints, and then it calls the fixed point algorithm because when you post the constraint, you may already have modify the domain of the variables and other variables, the variables which appear in the constraint. Right? So every time you post a constraint, you better be sure that you call the fixed point algorithm because some of the domains may already have been reduced in the initial propagation. Okay, now scheduling a constraint is extremely easy. The only thing that you do is you add that constraint to the propagation queue. Now the schedule method is called by whom? It's called by the variables, right? Remember, when a variable has its domain modified, through the listener, you are going to put some of these constraints inside. You are going to call this method schedule, and that method schedule is going to add these constraints on the propagation queue. No, you don't propagate them immediately. You put them on the queue, and at some point, the fixed point algorithm is being called, and then you basically propagate all these constraints. Okay, now, what is the fixed point algorithm doing? It's basically popping constraints and propagating them one at a time. Now, there is an interesting thing that can happen, right? So constraints can fail. So the constraints itself or the domain of some of the variables may throw an exception. And so what the fixed point algorithm is also doing is catching this expression. And when that happens, it has to clean the queue of constraints to propagate. You don't need to propagate these constraints anymore. Actually, you don't want them to propagate because you are going to go back to another state, another node in the search tree. And these constraints may not be relevant to be propagated at that point. Okay, so this is the fixed point algorithm in all its glory, right? So you have this propagation queue. As long as it's not empty, you are propagating a constraint. So you remove a constraint from the queue, you propagate that constraint. Now, if some of this thing fails, if there is a failure, you're going to catch this inconsistency exception that is going to be thrown. And what you do is you clean the queue and then you throw that exception again. And that exception is going to be caught by the search implementation, for instance, depth first search or another search. We'll see that in the subsequent videos. Okay, but here, what the fixed point is doing is that if there is a failure, it's going to catch that failure and stop propagating, clean up the queue, and then throw back the exception such that it's caught by the search procedure. All right, pretty simple, pretty elegant, right? So remember, this is one of the places where you can actually throw an exception. The domain listener here in a variable the domain can become empty, in which case you throw this exception. That's the place inside the variable where you can throw this exception. Of course, some complex constraints like the all different can throw exception themselves, right? But there will be some exception which are thrown by the constraint, some of the exception which are thrown by the variable when they become empty. Okay, look here, this is the implementation of the variable. You see when a min or a max or a bind, the variable is being bound, you will schedule the constraints on this list, and this is where we call the schedule method that I was just talking about in the constraint solver. Right? So every time some modification happened to the variable, we're going to schedule some of the relevant constraints that need to be propagated. All right, so far we have a very, very naive propagation. So I want to tell you is that you can improve it in two ways. The first one is to avoid redundant propagation, right? So if they are and mostly it's like, avoiding putting a constraint many times on the propagation queue. So for instance, if there are multiple variables in the constraints and they are all modified, so what's going to happen is that this constraint is going to be put multiple times on the queue. And so you're going to propagate it multiple times. And many of these propagations are probably completely useless because the first one is going to take care of everything. All right? So that's one of the things that we want to avoid. The other thing that we want to avoid is that at some point, some constraint may be satisfied. You know that they will always be true. Okay? At that particular point, there is no need to propagate them. And so you can actually say, hey, this constraint is satisfied. Don't bother actually propagating it anymore. It's always going to be true. All right, so how can we actually implement these things? The way to do this is to store in every one of the constraints two status variables. So it's going to be a schedule flag, and that schedule flag will mean that the constraint is on the propagation queue, and then a state variables which tells you if the constraint is active or not. Now, one of them is to be part of the state because it changes over time when you go down when we go to multiple nodes of the search space. The schedule flag doesn't have to be a state variable because it's only local to one step of propagation. It's never transferred from nodes to nodes. Okay, so these are the two things that we need to do, and this is the API for implementing these optimizations for the propagation. So the first two here are dealing with the schedule flag. You can set the schedule to a particular value, and you can find if the variable has been scheduled, it's on the queue or not. And active is the same thing. You can set the active flag, and you can actually find out if the constraint is active or not. Once you have this flag, you can do interesting things. So this is how we schedule the constraints. So if you send the constraint solver constraints, the constraint solver is going to see, hey, is this constraint active? Or you want to schedule the constraint only if it's active and it is not already on the queue. If it's active and if it's not on the queue, then you are actually scheduling it and putting on the queue. Otherwise, if it's not active or it's already on the queue, you have nothing to do. So what you do here is setting the schedule flag to true because now you know that the constraint is on the propagation queue. All right, so very simple, right? So when you schedule a constraint, you make sure that it's useful to actually propagate it and that it's not already in the queue because it's going to be propagated anyway. All right. All right, so obviously when you propagate a constraint, you have to tell the system, hey, I'm not on the queue anymore, so you set the schedule flag to false, and then if the constraint is active, you propagate it. The constraint may have become inactive because of some other reasons, obviously. So when you are cleaning the queue, you have also to reset the status of the schedule flag, right? This is something that I omitted before, when I was showing you the unoptimized, the naive propagation. But here, when you are basically popping things from the queue, you have to, make sure that the schedule flag is set to false, because otherwise the schedule flag will always, will still be true. And you would not put that constraint back on the queue in another node of the search space. So you have to make sure that when you clean the queue, you're also cleaning the schedule flag there. So this is all. We have essentially seen the entire constraint propagation of the constraint programming system. So we have been going from nothing, right? So the representation of sparse set to the fixed point algorithm in a couple of videos. And so now you should be capable of actually implementing all this. You can actually see everything as well in the mini CP system. And you can start adding your own constraints and coming really to the dark side. So stay with us, because there is one more important piece to do now. It's look at how we can implement the search and the search procedure. And this is going to be quite interesting as well.